bases? You probably have. You're probably not using it the way that it's technically meant to be used, and it probably doesn't mean what you think it does. In the area of chemistry, strong and weak refers to how completely an acid or base will ionize, whether or not it'll completely separate into its ions when water forms its little cages around it, or not. It does not talk about the concentration of the ions in the solution at all. Hydrochloric acid, HCl, for example, is a strong acid. When I put hydrochloric acid into water, it completely dissociates to form hydrogen ions, which of course sit on the water molecules around it to form hydroniums, and chloride ions. I can write the equation this way, or I can simply write HCl breaks apart to form H plus and Cl minus. In solution, when I put hydrogen chloride, hydrochloric acid, into water, 100% of it will break apart. Even if the hydronium ion concentration is diluted with lots and lots of water, 100% of it, or close to it, has still separated into ions. Calcium hydroxide is an example of a strong base. Now, calcium hydroxide, you might remember from your solubility rules, is not very soluble. In fact, hardly any of it wants to dissolve at all. But the part of it that does dissolve, the small amount that does dissolve, is dissolved in the form of ions. The calcium ion has separated itself from the two hydroxide ions and has been caged up by water molecules. And whatever part of the calcium hydroxide that is dissolved is in the form of ions. Calcium hydroxide, therefore, is a strong base. Now, if acids or bases are considered to be weak, that means they're not going to dissociate completely. They won't separate into their ions in water. For example, ethanoic acid, also called acetic acid or vinegar. When I put that into water, water likes to cage the entire molecule for the most part. It's very, very soluble. But only about 1 to 3% of acetic acid is actually separated into its form of ions. So it's considered to be a weak acid. Ammonia, NH3, which is a very common base, also is very soluble in water. But when water dissolves ammonia, it forms cages around the entire ammonia molecule. Very little will separate into ions. So ammonia is considered to be a weak base. Now, if these things are very, very soluble, obviously it's easy to make them very concentrated. It's also, we could add a lot of water and have them very diluted. And a concentrated or a dilute acid or base kind of gives us a feeling about whether or not it might be reasonably safe for us to be around or not. The terms strong and weak do not. Strong and weak, again, just tells us when it dissolves in water, is that acid or base in the form of ions, or has the entire molecule been dissolved into a shell of water molecules? So what does it mean to be strong or weak? Strong acids and bases ionize completely. That's all that that means. Weak acids and bases do not. Strong and weak does not refer to whether or not that the substance is safe or unsafe. It does not tell us if our solution is concentrated or diluted. And it does not tell us whether or not the substance is soluble or insoluble in water. And in common language, we tend to use it to mean these things. But for our points, that is not the truth. Strong acids and bases separate completely. And when we write equations with strong acids and bases, we will use one-way arrows to indicate this. For example, in the example mentioned already of hydrogen chloride, when it goes into water, it dissociates completely into hydrogen plus 1 ions and chloride minus 1 ions. To show that it completely breaks down, I write that equation with a one-way arrow. A weak acid or base will not break down completely, and so we would use equilibrium or two-way arrows. In the example we used with acetic or ethanoic acid, CH3COOH, this is a weak acid. So when it breaks down, Some of it will form hydrogen ions and acetate ions, but many of them will immediately reform acetic acid. All of these will be in their dissolved form in water, but to show that it is a weak acid, we use two-way arrows. So it's important for us to understand whether something's strong or weak because it's going to change how we write the equation for its dissociation. How can we tell if an acid's going to be strong or weak? Well, there's a couple of different ways that we can do this. For example, we can tell quite often by their formula. Now, there's a list here of strong and weak acids and bases, but they follow patterns, and patterns are much easier for us to learn than memorizing lists are. Based on their formulas for acids, if the acids are oxyacids, they contain oxygen, count the number of hydrogens and the number of oxygens and subtract. 4 O's minus 2 H's is 2. Anytime we get a number of 2 or more, that means it's a strong acid. 3 O's minus 1 H is 2. 3 minus 1 is 2. Again, a strong acid. If I subtract oxygens and hydrogens and I get a number less than 2, that would indicate that was a weak acid. 3 O's minus 2 H's, 3 minus 2 is only 1. Carbonic acid is a weak acid. What about for the acids that don't contain oxygens? Well, for the most part, our binary acids are strong acids. Hydrogen fluoride, however, is considered a weak acid. Remember, fluorine is the most electronegative element on the periodic table. Once it gets a hold of that hydrogen, it is not letting go. It does not readily want to ionize. So it's an easy one to memorize as the only binary weak acid. What about bases? Well, most bases are strong bases. Most bases dissociate completely if they have hydroxide in them. There's two exceptions to this: ammonium hydroxide and beryllium hydroxide. These are the only two hydroxide bases that would be considered weak. Also, all non-hydroxide bases, things like bleach, sodium hypochlorite, or baking soda, sodium bicarbonate, so all non-hydroxide bases fall under the category of being weak. Are there other clues we can use to determine if things are strong or weak? Well, yes, there are. We can look at pH. Remember that acids have low pHs? Well, my lowest 3 pHs belong to strong acids. So pHs of 0, 1, and 2 belong to a strong acid. pHs then from 3 up to 7 in neutral will be weak. Our big pHs, our highest of the pHs, belong to bases. So our highest 3 pHs, 12, 13, and 14, represent then strong bases. pHs from 7 of neutral up to pH 11 then would be a weak base. There is one other clue that we can use to determine things are strong or weak, and that's their equilibrium constant. Acids and bases will also have equilibrium constants. When the equilibrium constant is greater than the value of 10 to the minus 3 if it's for an acid, or 10 to the minus 3 if it's for a base, then we say that that acid or base would be strong. Equilibrium constants, Ka and Kb's, that are less than 10 to the minus 3 would fall into the category of weak. This would be a great point to pause this video and add these other indicators to your notes. These equilibrium constants that we talk about, my Ka and my Kb, are great ways to talk about relatively how strong or weak these acids or bases are. Obviously, it's not completely black and white. There's going to be ranges in the middle. When we look at any equation that is an equilibrium reaction, and we put products over the reactants to the power of their coefficients, that gives us our equilibrium constant, just like we had in the KEQ or in the KSP unit. In the acids and bases unit, we always show acids and bases as being in their aqueous form on the reactant side, and then the amount that's dissociated into ions on their product side. It's important to remember that in this unit, for acids only, we will only dissociate ever one hydrogen ion, one proton at a time. So for example, even though sulfurous acid, H2SO3, has 2 hydrogens. In its equilibrium situation, we only are interested in the first ionization, the first proton coming off. For bases, we'll break them apart in the ratios to which they are found. So, for the example of beryllium hydroxide, we're going to get 1 beryllium and 2 hydroxides. We'll have the concentration of beryllium ion times the concentration of hydroxide ion squared. We remember that the 2 in the coefficient becomes the power in the equilibrium expression. This will be over the amount of undissociated beryllium hydroxide ion. So for the acids, because we're only ever taking off 1 proton at a time, we actually have a little cheater formula we can use. So for any acid, hydrogen plus the rest of it being an anion, it will dissociate to give us 1 proton, an H plus 1, and the remainder of it, the anion. We see the exact same pattern here, 1 proton and the remaining anion. We actually are allowed to, it's a common convention, to write all acids in this unit as HA, breaking apart to give you H and A, where A represents the remaining anion, the remaining negative half once the proton's fallen off. Ka then would be the concentration of my hydrogen ion times the concentration of the remaining anion over the concentration of the acid, H times A over HA. Unfortunately, we have no such cheater formula for bases. For bases, you'll always have to look at the ratio that the ions dissociate to. This is a great example for us to work through together. Write the ionization equation and acid ionization constant expression for hydrogen hypochlorite, also known as hypochlorous acid. Then, if we're given the Ka for hypochlorous acid as 1.5 times 10 to the minus 6, and we're told the concentration of the hypochlorous acid is 0.02 molar, find for me the concentration of the hydrogen ion and the pH. There's a lot to do here. Let's start with step A, the ionization equation, and the acid ionization constant expression. The ionization equation just tells us in which ratio our salt, or acid in this case, breaks apart into ions. We can see that hypochlorous acid, HClO, will break apart to give us 1 hydrogen ion and the remaining anion, the ClO minus ion. It would also be acceptable to write the cheater formula, HA breaks down to give us H and A. In this case, however, we have the formula in front of us. We may as well use it. I know that I'm going to use two-way arrows here. We have a couple of clues that let us know this. Comparing oxygens to hydrogens, we get enough difference of less than 2, and hypochlorous acid is a weak acid. Also, because we're talking about a Ka and a Ka value of less than 10 to the minus 3, again, we know this to be a weak acid. Anytime we're dealing with a weak acid, we use two-way arrows. Now they want us to write the acid ionization constant expression. That's a big, long word, but the moment we see constant, we think K. So my Ka expression in this case will be Ka equals H times ClO minus over the concentration of HClO. This is my ionization equation. It's an equation showing how the acid ionizes. This is my Ka expression. Again, we have a balanced equation and an equilibrium expression. What we're missing is the work in the middle. Now, they've given us some information. We know the value for Ka. We know the value for the concentration of HClO. They want us to find the value for hydrogen and then also the pH. Organizing my thoughts here, I know the concentration of my acid is 0.02. They don't tell me the concentration of hydrogen or the hypochlorite ion, but I can see from the balancing that they're going to form in a 1-to-1 ratio. I can't assume that all 0.02 moles breaks down. There's two-way arrows here. This is a weak acid. Only some of this is going to dissociate. So we're going to let X stand in place of the amounts of hydrogen and hypochlorite. Let's substitute this and our value for Ka into my equilibrium expression. Substituting the values 1.5 times 10 to the minus 6 in place of Ka, my concentrations of hydrogen and chlorate both being X, and my concentration of hydrogen hypochlorite being 0.02, I can simplify this to say X squared over 0.02 is equal to 1.5 times 10 to the minus 6. Solving for X, and we get an answer of 1.73 times 10 to the minus 4. Now, we've solved for X. Let's think about what X is. Over here, we have an X under the hydrogen. X is standing in place for the concentration of hydrogen. That's one of the things that we wanted to solve for. So now we can say that the concentration of hydrogen, which we know to be X, is equal to 1.73 times 10 to the minus 4. Concentration is expressed in moles per liter, or molar. We've also been asked to find pH. Well, this is easy for us now because from the pH square, we know that the pH is equal to the negative of the log of the concentration of H. The negative of the log of 1.73 times 10 to the minus 4 is 3.76. We should always ask ourselves if this makes sense. pH is less than 7 are acids, and pH is between 3 and 7 are weak acids. We've already established that this is a weak acid, so this does indeed make sense. Another way of deciding how much of an acid or base dissociates when it's a weak acid or base is to use percent ionization. Percent ionization tells us what percentage would actually break apart into ions. Consider this example. Suppose we have a 0.001 molar solution of acetic acid, and that acid will be 5% ionized. Find the hydrogen ion concentration and the pH. Again, we know this is a weak acid because it's acetic acid, which we've already discussed as a weak acid. But even if they had named some obscure acid that you don't know the formula for, we could have used the cheater formula. HA breaks down to H and A. 5% ionization is the clue that it's a weak acid. Remember, strong acids are completely ionized. So again, we see HA breaking apart to give us H and A. If you know the formula for the acid, feel free to use it, but you're always welcome to use the simplified version. Let's see what we know about this acid. Well, we know its concentration is 0.001 molar. So under HA, I'm going to write its concentration. We don't know the concentration of hydrogen or the anion. We've been asked to solve for this. Again, from the ratios, we can see that they'll form an equal amount, so we'll call them both X. What clue did they give us to solve for X? In this case, they did not give us a pH as a starting point. We could have used the pH square then. They did not yet give us Ka. In fact, we're going to be asked to solve for it. What they gave us was percent ionization. 5% of this acid breaks down. 5% of the concentration of the acid is the same as saying 5 out of 100, or 5%, times that number. So I'm going to go 5 divided by 100 times the concentration of the acid, and I get a value of 5 times 10 to the minus 5. This is the amount of hydrogen that we're going to have. So now I know the concentration of my hydrogen ion. It's X. It's 5 times 10 to the minus 5. Incidentally, X also is the concentration of my anion. Now that we have this information, they asked us to find the pH. Well, this is a pretty easy step because pH is just the negative of the log of this value. Substituting, the negative of the log of 5 times 10 to the minus 5 is a value of 4.3. We've also been asked to solve for the Ka. So from this balanced equation, we can write an equilibrium expression. Using the same pattern we've used for all equilibrium expressions of products over reactants, Ka is going to be equal to H times A over HA. Since H and A are the same value, we're going to substitute 5 times 10 to the minus 5 times the sulfur squared over the concentration of the acid, 0.001. Doing the math, we end up with a Ka value of 2.5 times 10 to the minus 6. Again, a number less than 10 to the minus 3, which corresponds to the Ka for a weak acid. So knowing whether or not an acid is strong or weak allows us to apply our knowledge of equilibria to figuring out the concentrations that we can then use with our pH square. This is a big concept and will require significant practice. There is lots of practice and explanation in your textbook on pages 644 to 658. There are several questions for you to do out of your textbook that will be good practice for you, especially on Ka and Kb calculations. Also, in your workbook, there's a section called Level 2 Questions, and I want you to do questions 1 and 2, which will help you to practice using percent ionization. You will notice that for the workbook questions, I've included the answer on the following page. This is a big concept and will take us a couple of days to practice. As always, if you run into any difficulty or you'd like for me to demonstrate how to solve a problem for you, please feel free to contact me.